In this video lecture, we will explore the concept of uncertainty principle from a new perspective. For that, we should be familiar with the term wave packet. According to de Broglie, a single particle motion is expressed in terms of a wave called de Broglie wave, whose wavelength is lambda equal to h by p. If you calculate the velocity of the de Broglie wave, which is equal to c square divided by v. Here c, the velocity of light, v is the velocity of the particle. This is not an acceptable one. To solve this difficulty, quantum mechanics proposed the concept of wave packet. A wave packet is an envelope that contains more number of waves with different wavelengths. These waves undergo constructive and destructive interference. Finally, the entire wave packet can move at a particular velocity called group velocity. Group velocity v suffix g equal to d omega by dk, which is our particle velocity. Now read out this statement. A particle is most likely to be found in a region where the amplitude of the wave function is maximum. If you see this wave packet, these waves are having maximum amplitude. The particle is most likely to be found only in this region. That's the meaning of this statement. When the size of the wave packet is small, this is a smaller sized wave packet, we can easily find the position of the particle, that is location of the particle. The potential reason is, in a smaller wave packet, the region with the number of waves of maximum amplitude is narrower. Say this is narrower region. Therefore, in this case, we can find the position of the particle exactly, but if you measure the momentum at the same instant of time, there is some error in calculating momentum. That is delta p. Error in calculating momentum. We can measure the position accurately, whereas the momentum is not measured accurately, error is taken place. Because in the smaller sized wave packet, the wavelength is poorly defined. According to de Broglie concept, lambda equal to h by p. Therefore, p equal to h divided by lambda. If lambda is poorly defined, momentum is also poorly defined. Therefore, error is taken place in calculating momentum. Suppose the size of the wave packet is very large, we won't predict the position of the particle exactly, but we can calculate momentum because lambda is well defined in larger sized wave packet. At that moment, error is taken place in calculating the position. Now we may go to the uncertainty principle. It is impossible to measure simultaneously and accurately the values of particular pairs of physical variables that describe the motion of an atomic system. This is our uncertainty principle. Consider the physical variables x and p. These two are useful to describe the motion of an atomic system. If you measure position first, there is some error in calculating momentum. If you measure momentum first, there is some error in calculating position. Anyway, at the same instant of time, we cannot record these two quantities. Therefore, we can write delta x, error in calculating position, into error in calculating momentum is greater than or equal to h cross by 2. This is our uncertainty principle. Now we should talk about the origin of uncertainty principle. The origin of uncertainty principle is wave nature of matter and non-commuting property of operators. These two are totally responsible for our uncertainty principle. Here, wave nature, that's well known to you. Suppose a particle is moving with velocity comparable to the velocity of light, that particle is having both particle nature as well as wave nature. In the quantum limit, if you talk about subatomic particles, say an electron is taken for our consideration, the velocity of the electron is 1/10th of the velocity of light. Therefore, it is moving, it is having dual nature. According to Davis and Germer experiment, we can confirm the wave nature of electron. If you measure position first, there is some error in momentum. If you measure momentum first, there is some error in position. Since these two operators are non-commuting means x comma p equal to xp minus px not equal to 0. From this we can write xp not equal to px. You know the value xp minus px, which is equal to IH cross. These two operators are not subjected for commutation. If two operators are commuting, that should satisfy the rule AB equal to BA, AB minus BA equal to 0. Then the operators A and B are called commuting operators. Here X and P are non-commuting operators. Then only they may obey our uncertainty principle. Now if you consider the commuting operators, L square and Lz equal to 0. The meaning is L square Lz minus Lz L square equal to 0. L square Lz equal to Lz L square. See here, L is our orbital angular momentum. L square means Lx square plus Ly square plus Lz square. L is our orbital angular momentum. Square of the orbital angular momentum is L square. The square of the orbital angular momentum commutes with one of its components, that is Z component. Therefore, L square Lz is equal to Lz L square. These two operators are commuting. Therefore, we won't apply our uncertainty principle for these two operators. The meaning is, at the same instant of time, we can record these two quantities with perfect accuracy. L square and Lz are measurable simultaneously with perfect accuracy. Now we should know the reason. How do we measure? If two operators are commuting, they must possess or they must hold simultaneous eigenfunction. See here, A is one operator and is allowed to operate on psi, provides one eigenvalue small a and the same eigenfunction psi. B is another one operator allowed to operate on psi, provides some eigenvalue b and the same eigenfunction psi. Now psi is a single eigenfunction and is allowed to operate with two operators a and b separately in order to provide the eigenvalues a and b respectively. Now we can say these two operators are commuting with each other, AB equal to BA. If two operators are commuting, then only we can get a single eigenfunction. L square and Lz are having only one eigenfunction, therefore we can measure these two quantities simultaneously with perfect accuracy. Then we won't apply our uncertainty principle for this case. Suppose the operators are non-commuting, we can apply our uncertainty principle. If two operators are commuting, we won't apply our uncertainty principle. Now, see the relation delta E delta T greater than or equal to h cross by 2. According to origin, if two operators are non-commuting, we can apply our uncertainty principle. Here, E is our energy operator whose value is I h cross dou by dou T. What about T? T is a parameter. It is not an operator. Then how do you allow it to present in the uncertainty principle? That's a question. Here, T is our lifetime. In the excited state, suppose a system is stayed for short interval of time, that is lifetime, short lifetime. If a system is having short lifetime, then the uncertainty in energy is maximum. At this stage, we can get broader energy spectrum with the blurred aspect. Energy spectrum is not clear, but broader. Broader spectrum we can have. Broad spectrum we can have. Suppose the lifetime is long or more. If the system is in the stable state for a long time, delta E is minimum. Now we can get sharp energy spectrum. In this way, we should include delta T in the uncertainty relation. Therefore, T is not an operator, it is a parameter. Now, think about this equation. From the undergraduation onwards, we are studying this relation delta E delta T greater than or equal to h cross by 2. What's the meaning of this inequality? We should clarify. If the wave packet is Gaussian, the uncertainty is minimum. Uncertainty is minimum. At this stage, we should write delta E delta T equal to h cross by 2 or delta x into delta p equal to h cross by 2. If you consider the relation position and momentum, product of error in calculating position and product of error in calculating momentum is equal to h cross by 2. If you write delta j into delta theta, which is equal to h cross by 2. If the wave packet is Gaussian, the uncertainty is minimum. At this stage, we should use the equality sign. If the wave packet is triangular, rectangular, etc. That means other than Gaussian, we should write the relation del x in del p greater than h cross by 2. Here uncertainty is maximum. Uncertainty is maximum. See here, if the wave packet is Gaussian, we may get minimum uncertainty. Therefore, we should use equality symbol, equal to del x del p equal to h cross by 2, del j del theta h cross by 2, del e del t h cross by 2. If the wave packet is triangular or rectangular or some other, uncertainty is maximum. At that stage, we should use delta x delta p greater than h cross by 2. But we do not know the nature of the function. So in general, we are using del x del p greater than or equal to h cross by 2. Another one clue I would like to give. If the wave packet is triangular, rectangular or some other, the delta x value is minimum. Error in calculating position is minimum. We may calculate the position with maximum clarity, but delta p is maximum. But here the chance is 50-50. That's all about the usage of wave packet. But often we are familiar with the term canonically conjugate variables. What are canonically conjugate variables? Have you ever heard the term canonically conjugate? Canonically conjugate variables. X comma p, e comma t, j comma theta. These are called canonically conjugate variables. The measurement of one variable may produce error in other. Therefore, these two are interlinked. Then only we can call these variables as canonically conjugate variables. Able to follow? If you measure one quantity, that may affect the measurement of other. Since these two variables are interconnected, such variables are called canonically conjugate variables. You know the unit of del x into del p, that is joule second, unit of Planck's constant. Now we may arise one question: will we apply the uncertainty principle in the classical limit? We know the origin of uncertainty principle. One is wave nature of matter and another one is the availability of non-commuting operators. In the classical limit, there is no talk about wave nature. Furthermore, if you use our uncertainty principle, delta x into delta p greater than or equal to h cross by 2. Here we may replace momentum p equal to mv in the classical limit. In the classical limit, mass of a particle is a constant. There is no change in mass. But in quantum aspect, we may say variation of mass with velocity. If a particle is moving with velocity comparable to the velocity of light, its mass is not a constant, it is also a variable and is represented by the relation variation of mass with velocity, m equal to m0 divided by root of 1 minus v square by c square. If you consider the mass of an electron, it is not a constant. Rest mass is a constant. In our Clark's table, we are observing the rest mass alone. But if an electron is making its motion, its mass is not a constant, it is also a variable, which is given by the relation m is equal to m0 divided by root of 1 minus v square by c square. Here m0 is the rest mass, m is the moving mass. But in the classical limit, mass is a constant. Now put this del x, instead of this del p, we may write del v, because mass is a constant, h cross divided by 2m. In this relation, mass of the classical body is huge when compared to the value of h cross. So this factor is negligible. At that stage, there is no talk about the product of errors, which means that in classical limit, simultaneously we can measure the two quantities. So we won't apply our uncertainty principle in our classical limit. These are all the basics of our uncertainty principle. Thank you.